So this is our project's assignment, and this file is our project's report. We can see it step by step, our project assignment and our reports, results and comparisons. So project description is: the aim of the project is to implement data management components of the city mobility platform aimed at managing a short-term rental of shared electric vehicles across different cities in Italy. The system must track 4 types of the data, which are users, trips, stations, and events generated during the trips. This data must adhere to the following specifications. We will use the 3 main types of the databases, which are relational database management system. We will use the PostgreSQL for that, and documentary data. For the documentary we will use the MongoDB, and for the graph we will use Neo4j. So first, and for most queries, which is user identify users to mobility platform, each user has its name, surname, birth date, and the country origin. So we have our data table and data tables fields. The next one is station represents points of the interest tracked by the mobility platform in which users can deposit or take the vehicles. Each station has a name, it's situated in the specific city and has maximum capacity of the vehicles it can be stored. The next one is trips identify single, complete trips conducted by registered user. Each trip is associated with the user with the start station and end station, and of course start time and end time, well as a total cost. Events represented events 0, or it can be more, that can occur during each trip. Even each event is associated with a trip, and time step describing when the event happened, the type of the event, GPS, error, battery, and the delay, and the value of the described the event. So part 1, comparing the relational and document models. Firstly, data modeling. We need to design a database for the specific data management system, specifically design the relational schema and design the document schema. So what we did, this is our project's report. We can see in here. So firstly, we created the 4 tables and fields for the relational DBs, which are users and the stations, trips and the events. Users includes ID, name, surname, birth date, and the country. Stations includes ID, name, city, and capacity. So trips includes ID, user ID, which is foreign key to the users. Start station ID related to the station table, and station ID of course related to the station ID, station table. Start time and end time, which is timetable types of the fields, and total, the last one is cost. And the next table, DB table, is events, includes ID, trip ID related to the trips, and time step, event time step, and type and value. Index is created. So firstly, all of the connections related to the foreign key, because it is a referencing approach, we use it for the relational databases. This approach's advantages are: data is not repeatable, schema is easy to update because the tables are relatively connected. So there is some drawbacks of course of the referencing approach, which is it requires many join operations. For example, if you want to get users, trips, stations, we need to request them separately, like the select from, some kind of join user, join trip, join station. Every time we need to use join requests. So for the MongoDB, we can see instead of the create 4 tables, which are users, stations, trips, and events, we just created users, stations, and trips. events included trips. So why? Because event always belongs to the trip. It doesn't need to exist independently. So for users and stations case, many trips repeatedly. If we embedded them, data may repeat millions of the times. So comparison of the part 1 is we decided referencing system approach because all related data is stored separate tables and it is good for linked and standard normalized approach. No data duplication and simple updates and strong integrity. So aspects of event storage, so our PostgreSQL save them separately table and Mongo saves it embedded in trips docs. For the filtering case, PostgreSQL uses the joint events, Mongo uses direct array filter. And if you want to change schema logic for PostgreSQL, we need to update all of the rows tables with the alter command. And for the MongoDB, we don't need to any migration tables. So for the aggregation case, PostgreSQL uses group by ID. For PostgreSQL needs to group by ID filter functions. Mongo uses just a $score group function pipeline. They are almost the same alternatives, which are data consistency case PostgreSQL based on the asset method and MongoDB eventual method to use it. This is the main comparison summary of our document and relational schema models. The next task is, after the data modeling, query implementation. We need to implement the following queries of the both proposed designers, means relational and the document based. So first query is return all trips with user information, starts and end station names. Second query, return all users with the number of trips performed, average trip duration. The third query is return all stations with number of the trips starting here and number of the trips ending there. And the fourth query is return all trips that contain at least one event with the type error. We need to provide in our report comparison of the efficiency of our implementation of the queries according to both designs, which are relational and document, as well as scripts or similar resources for the actual implementation of the queries. In our comparison, generate simulated data to populate our schema and evaluate the scalability of our implementations according to the following parameters, which are 1,000, 10,000 to up to 50,000 or 50k number of the users, and the number of the trips included for the implementation 10k, 50k and 100k, and of course number of the events per trip. We can use 0 to 5 and 10 of number of the event of each trip. So how we implemented them? Our scripts included in our codes, which are part 1's folder, queries PostgreSQL and queries MongoDB separate files, and we mentioned in here some parts of the code samples. So firstly, we did the query 1 based on our data sets, which are users. We just simulated and generated simulate data with our CSV formats, which are users separately, stations, trips. So we used these codes, and for the PostgreSQL we got some results, which are all trips with the user's information and start and end station names. This is our main queries. So summary for the PostgreSQL, we used 3-way join commands join for the users, join for the station, start station, join for the end station. And our result took the 0.90 seconds for the 50k users and 100k trips. And we used this for coders for the MongoDB. Of course, we used 3 times of the lookup, which is alternative of the query, join query of the PostgreSQL. We used lookup for the MongoDB, and our result was a little bit longer, a little bit bigger, because we use it, of course, 3 times of the lookup function, and the result was significantly slower than PostgreSQL at the scale, and totally took 908 seconds at 50k users, 100k trips. So why? Because firstly, lookup designed for the heavy relational style joined at the scale, of course, and that's why the large data sets, that's why with the large data sets it becomes slow compared to relational databases. So for the first query, PostgreSQL wins than MongoDB. So the next query is all users with the trip counts and average duration we need to implement, we need to get. So for the PostgreSQL, we use this select user ID and user name and trip ID as a count, and we call it a trip count, and we calculated average duration with the difference between the start end and start time, and we changed its format to the minutes, it's minutes, and we use it from users left join, because we are calculating the users table, because that's why we use left join. Trips on the user ID equals to trips related to user ID, and we group filtered by user ID, username, and user surname. So, and almost the same logic for the MongoDB, of course, with the add fields and the group fields, which are user ID, trip count, sum. We calculate the average minutes of the duration and difference between the end time and the start time. And what was our summary for that query? Showed PostgreSQL with the 50k users, totally 0.93 seconds because of the left join. We can see in our table. Query 2 is here, 0.09 seconds because of the left join and group by ID filters, and of course MongoDB case showed almost 40 seconds. You can see in here for the query, MongoDB query 2. So the results almost the same. That's why our decision was the both of them are acceptable. So the third query is all stations with the trips starting and ending there. We use it for the PostgreSQL 2 left joins on the trips, which are station ID and end station ID grouped by the station. But unfortunately, it was on my PC happened at the bottleneck, especially at the 100k trips, and PostgreSQL query for the query 3 takes 18, almost 19 seconds. Why? because operations use 2 times again, which is a left join, and each time scanned full the table. And this is the main reason of the result. And our suggestion is, we wrote our suggestions, which is the firstly materialize that we use, or the and the index function. So firstly, we can describe the index function. It works like the index section of the book. So instead of scanning full table row by row, PostgreSQL can directly jump to the rows matching a specific station ID. If we create indexes on the start station ID and end station ID, the database can locate relevant rows much faster. This reduces full table scans and speed up join operations and significantly improves the query performance. This is my personal suggestion. And for the MongoDB case, two separate group pipelines, one per direction, then merge it with the Python because I used the PyMongo library, and the result was 9.11 seconds at the 50k users and 100k trips. So instead of the repeatedly scaling multiple collections, Mongo processed in the streaming pipeline and the filtered groups every table in just one pass, and it returned aggregated results. So for that case, MongoDB is much more faster than PostgreSQL on my results. So the last query was for the first task, trips that at least one error event we had to show. So we use it for the PostgreSQL distinct function, and we got the data sets from the trips, and we filtered it error type trip. In the PostgreSQL, since events are stored in the separate table, we need to do a join between trips and events, and then we filtered where events.type error. That means DB has to connect two tables and it match rows through foreign keys, and the result was around 0.220 seconds. We can see for the 50k users and 100k trips and 5 events. And the MongoDB performance, we used this main query code. Events are embedded inside of the trip document as an array, as we talked before, so we can directly query with the events.type equals to error. That's it. And that command, Mongo scans array inside each document, checks if any event has type error. There is no any kind of join, there is no any kind of cross collection lookups, and the result was significantly difference than PostgreSQL, and it was 0.165, almost 2 times faster than PostgreSQL. For that query, we can decide both of the DB performance acceptable. So the next query is schema evolution. We need to describe our report how we would handle this future schema modification, requiring that all events of the type battery include additional field battery level. It means we need to add the additional one field, which is name or is battery level, an integer with values in 0 to 100. This is the limit of the numbers field. We need to provide the comparison of which implementation of the DB management system, relation or document, would exhibit better availability in relational to the design our proposed. Okay, what we did for that case, we can see in here our all 4 queries comparisons with the graph-based format. We can see in here the graphical version, significantly which one is the better than which one and which one is acceptable, like these collections. And our summary, we mentioned it in here. As we talked orally, we wrote in here the concepts. So the next we can see the next task, which is schema evolution. So we did for the PostgreSQL, we wrote alter table for the events, and the add column, the battery level, which is a data type, it was integer, and for that case we checked the battery level between the 0 and 100. And in the PostgreSQL, since events are stored in a separately table, we need to do join. So this command adds the column to all event rows, not just the battery, but existing rows get null for battery levels. It means we have some problems. Advantage points are we can just easily add with the alter table with any kind of the column, but the main problems are, firstly, DDL migration requires. DDL means data definition language. It means we need to write that alter table, create table, add column commands for each create operation. This is the main problem. Every time it logs the table during the alter. The next one is all existing battery rows must be backfilled with a value. It means we go through all existing rows and assigns a value to battery level. And the third problem is it requires a maintenance window on multi-state migration. And it means every row has valid value or schema becomes strict again. And the next problem is non-battery rows, like maintenance window of the multi-step migrations. It means every row has a valid value or schema becomes again the strict. So for the MongoDB case, extremely easily actually, because no any schema migration needs at all. Just simply insert new battery events with the field, type of the battery with the timestamp or battery fields, and old battery events without any battery level remain valid documents. So comparison of that case, we choose it availability. Means Mongo is as we see, clearly superior for this type of the schema evolution, because the document model allows adding optional fields to a subset of the embedded documents without any migration, and table looking or backfill operations, of course. And PostgreSQL, the main problem is it requires DDL changes that affect the entire table and can disturb production workloads, of course. So winner is, for that query, MongoDB, because it is a schema on read flexible DB management system. Next query is Spark-based implementation. We need to provide Spark-based implementation for the query 2, which is in here. Return all users with the number of the trips performed and average trip duration. We need to compare the Spark-based implementation of the query with the in-database one. We must provide in the report comparison of the efficiency, our implementation of the query, as well as scripts, of course, or any kind of similar resources for the Spark implementation. So we can adopt any solutions of the choice for the implementation, including either or both methods can directly work with RDD or higher level abstractions, for example, stack data frames. In our comparison, we need to generate simulated data again, because we have already the read data sets, populate our schema, evaluate scalability of our implementations according following parameters, which is 1K, 10K and 50K number of the users, 10K, 50K, 100K number of the trips, and 0 to 5, 10 number of the events. This is the last part of the last part of the first part. Okay, this is our solutions and the comparisons, which is we used like these commands for the Spark SQL. We firstly loaded our trips from our trips.csv file, and explanations. Firstly, we can explain our codes. We start by loading the data into Spark, and we read these CSV files because it's given in this query 2, as we said before, and Spark loads as a data frame. It's a data frame, meaning distributed tables that can be processed in the parallel across cluster. And the next step, we work with the trips data, and we create new data frame called trips2. This is our the data frame, and here we add new column called duration or durmin. It calculates by taking end time difference between the start time, and then we do aggregate steps, and we group the data by user ID. For each user, Spark calculated two main things. Firstly, the number of the trips using count of the trip ID, of course, and secondly, the average trip duration round to decimal places. So at this point, we have one row per user with the summarized trip statistics, and after that we move join step. We take user data frame and left join user ID for the aggregation. So this means we match each user with their trip stage statistics, and finally we drop the user ID column from the aggregate table. So now about the performance result. With the test up to 50k users and 100k trips and 5 events per trip, we show that in here Spark showed 0.181 seconds, PostgreSQL takes the 0.09, and Mongo takes the 0.4 seconds. So, conclusion. For the main idea is Spark is doing distributed computation, and it's powerful for the scaling large data sets, not just the 50k, 100k, but the million plus actually. For that small case and relative data sets, of course, Spark itself makes it not too much, but slightly lower than PostgreSQL, we can see in here. So, but PostgreSQL wins because it's highly optimized for relational aggregations on the moderate size data, and Mongo a little bit slower because it has a deal with document scanning and less efficient for aggregation platforms.